presentation, we're going to analyze the crane failure and provide new solution to prevent this in the future.
So, the sequence of events began when a Model X Bus 47 from Red Wing Lifts was ordered on 10th February 2017. The crane arrived on 19th February with its installation kit missing, which was later found. On 24th February, the crane began installation by Travolta Technical Limited, hired by the contracted installer. There were many issues with the installation. For example, the wrong tightening torque was used on the nuts and bolts, and one of the 8 bolts was missing and replaced with an identical part. A new base panel was made to fit the crane onto the plinth. The installation completed on 28th February and was commissioned on 14th March. An overload test was conducted by a Red Wings engineer with no issues, and the crane was commissioned for use. On midday 5th April, John Tuttle was loading pallets onto the truck when the crane collapsed during rotation and fatally injured Mr. Vance, the factory manager.
To analyze the failure, the design has been criticized. First, in regards to the crane installation, nuts should have a higher grade than bolts compliant with the British standard. However, nuts of grade 8 and bolts of grade 10.9 were used. Additionally, improper type of bolts was included in an installation kit provided by the manufacturer. Due to the lack of communication, the tightening torque values were unknown. Torque of 546 Newton meters were used instead of recommended value of 350. This will cause the preload to decrease over time, increasing the chance of separation between the base plate and the plinth. On the side, one of the bolts was missing and a bolt from a similar crane was used to replace it. This bolt can cause an inconsistency within the mounting, resulting in an uneven distribution of stress across the base and plinth. Base plate and plinth size does not match as the plinth had not been modified properly. This violates Act 58A of the Lawler, which states that the size of the plinth should be sufficient for the crane and any extra workers or work equipment. The Lawler 303 and 304 and Red Wing Lifts manual states that all cranes must be tested by a competent person before first use. However, high-trick cars used the crane before the loading test and commissioning, hence this regulation was breached. Lawler Cost 160 states that the lifting equipment should be positioned and installed to prevent crushing when it is in its extreme positions. This was not considered as the crane collapsed and fatally injured a worker. In a weekly inspection, one of the lifting straps was missing, so they were replaced with lifting chains. HSL report proves that there was no failure in lifting chain.
We shall now look at what went wrong and how it happened. On February 28th, the crane was successfully installed. The fasteners used to secure the crane to the plinth were tightened to 546.12 Newton meters of torque instead of 560 due to a wrongly calibrated torque wrench. This equated to 135.5 kilonewtons of preload, which was also equal to the clamping force whenever no external loads acted on the system. We also determined the critical force required to cause the separation of the base plate and the plinth, shown in the diagram in the previous slide. That force was equal to 150.6 kilonewtons. Whenever the crane lifts a battery pallet, there is an incident tensile load that acts on the bolts. On March 14th, a safety test was carried out by a senior engineer from Red Wing Lifts, where the crane's boom was overloaded by 33%. This meant that the maximum load sustained by the bolts at the base rose to 249.33 kilonewtons. The preload also causes an additional axial load on the bolt. Having solved for the relevant parameters, we were able to determine the resultant tensile load on the bolt, and we found that value to be 160.4 kilonewtons. Since this value is significantly larger than the minimum force required to cause a joint separation, which was 150.6 kilonewtons, we can safely assume that the bolts and nuts assembly became loose and a gap was formed in between the two plates. In order for this to have happened, the threads of the fasteners, which were under immense stress, must have been deformed or significantly weakened. With the situation gradually worsening after each subsequent crane operation, on the 5th of April, the nylock nuts threads finally failed, leading to the crank collapse. Aside from using lower-grade, weaker nuts than the ones recommended for use with the given bolts, the main cause for failure was the fact that the nuts were in fact under-tightened. Had they been correctly preloaded, the accident would not have happened.
There are 4 main parties involved in the failure of the crane. Red Wing Lifts were responsible for supplying the correct equipment and specification, which they failed to provide. Installation manuals and torque data were also not given despite multiple requests from the Hytric Cars branch manager, highlighting their unprofessionalism. Lack of communication between the company and their senior engineer regarding the load limit request by Hytric meant that there was no load limit set, which means that they can be held accountable for gross negligence, breaching Act 337 of the law. Hytric Cars lacked patience, rushed the installation process despite the absence of data, and used the crane before commissioning. There were many instances where the Health and Safety Acts of Lola were breached. Example, the miscommunication between Stryper and Anderson regarding the setting of the limit load, the misuse of the crane, and the poor working conditions at the time of the incident, where Mr. Vance was struck by the crane despite standing outside the mark zone. Another example of gross negligence. For the Stryper, Andrew with the technical, both severely underdone the preload with 560 Newton meters, so both can be held accountable for contributing negligence.
So while Express 47 cranes are designed to be mounted at the back of a lorry, placing them at a static location is still possible, according to the manufacturers. Nevertheless, the adaptation to the static mounting requires thorough redesign of the base of the crane. The new suggested design aimed to improve the original design to make it more versatile to both static and dynamic mounting. This will not only improve safety, but also make installation easier. Therefore, improvements in both user experience and customer satisfaction is achieved. We have developed a design specification based on the problems and the need of the problems that we identified. The new design will be based on the aspects and the criteria of the design specification.
To improve upon the existing design, two main ideas have been formulated. The first idea involves changing the base plate and plinth. Their surface areas are to be made higher, and the base plate's mass should be made greater to increase the stability of the crane. Both will have a square surface area with a new arrangement of bolts going all around the perimeter. This ensures that the load is distributed evenly as the angle of the boom changes. The bolts being used are M24 bolts of grade 10.9, and the nylock nuts will be of grade 10. In the case of another failure, the bolts should fracture first rather than the stripping of the nuts, making the failure more apparent and allowing for proper action to be taken. The second idea involves putting a fail-safe system in place to ensure that the crane doesn't collapse if the nuts and bolts fail. This fail-safe system consists of 4 zero-member legs that should be able to withstand the force of the crane and any reasonable overload. The legs will be attached to the square base plate on one end and to the ground on the other end. The members are all a hollow rectangular cross-section. To assess whether these legs would fail under the overload, some assumptions have been made. Firstly, it is assumed that the 3D crane system is a 2D system, where the weight of the crane is supported by 2 legs. One of the legs would be in tension, whilst the other would be in compression. The second assumption made is that the member in tension is neglected, meaning that the resultant crane load is applied on one leg. By doing this, large safety margins are created. After these assumptions, the system becomes easy to solve, and through the use of Macaulay's method, it can be seen that there is little deformation occurring throughout the member. This is also supported by ANSYS simulations, which show exaggerated effects. This means that the members should not fail due to bending. By using the buckling equation, the buckling stress can be calculated as 440 megapascals. From ANSYS, the axial stress, which correlates to buckling, is 30 megapascals when structural steel is used as the material of the legs, thus proving that the members should not fail due to buckling. Therefore, the fail-safe system would not fail. From these calculations, structural steel has been chosen as the recommended material for the base plate, plinth, and legs. To assess the feasibility of these new designs, a rough cost analysis has been done. The total mass of the 3 components comes to 13.5 tons. The average cost of structural steel is £1,350 per ton. Therefore, the cost to implement the designs using structural steel as the main material is £18,200. This is considerably less than the cost specification, and so the designs are feasible.
In addition to the main design ideas, a number of small changes can make improvements to help lower the chance of failure. Firstly, thermal sensors and 360 cameras can be installed in and around the crane. These can be used to observe what is going on at all times, as well as a safety mechanism, by sensing workers and stopping the crane when needed. To add to this, the crane could be installed with a remote control, allowing full operation from a safe distance. Furthermore, nuts and bolts could be galvanized to prevent any form of corrosion, and thread lockers could be used to secure the nuts and bolts. Finally, in regards to the operation, the loading area could be made much bigger, and the workspace should be organized to prevent any potential obstacle. These are our references.